In our last video on block diagrams, I introduced the concept of feedback in a system. Today, I want to show you how we can use what we have learned about systems modeling and block diagrams to get a system to behave the way we want it to. In other words, I want to show you how we can change a system on purpose in order to get the output of a system to act in a way that's more desirable for some given input. In order to start off and give us an example that we can follow, I'm going to introduce a device called an inverted pendulum on a cart. Here's the setup. We have a rod that is pinned so that this rod can rotate on its pin. The pin, in turn, is connected to some kind of a vehicle. This is shown here as a mass that is on wheels, and this cart, this mass on wheels, can move. In our case, I'm going to refer to this device as the car, and this part I'll refer to as the pendulum or the rod. I'm going to assume that the car is electric, so that the car's input signal is a voltage and its output is going to be a force. Now I know that usually we take the output of the car to be velocity, but if you remember back when we first started modeling electric motors, I also derived the transfer function of an electric motor between the voltage and the torque. So for today's example, I'm going to take the output of the car to be force on the bottom of the pendulum, because that's going to make our pendulum modeling case a little bit easier. Now the pendulum itself takes the force applied to its bottom from the car, and it converts that into an angle. The goal of this whole system is to figure out what kind of a voltage we can apply to the car in order to prevent the pendulum from tipping over. In other words, we want this car to balance the pendulum. Now, I'm not today going to go through the whole process of how we find the differential equations that relate voltage to force and relate force to angle of the pendulum. And I'm also not going to go through the process of how we find the transfer function from those differential equations. Instead, I'm going to start by giving you the transfer function, and we're going to take a look at how we can solve this problem of figuring out what voltage will balance the pendulum on the car. Now, before we start doing some calculations, let's just think about this system intuitively for a moment. What will happen if we apply a step input to this system? In other words, what would happen if we suddenly applied a voltage to the car? Clearly, we can see that the pendulum would fall right over as soon as the car starts to move. Let's take a moment and see what this looks like when we actually calculate the step response of this system. In order to find the step response of this whole system, we need the transfer function. Let's start with the transfer function of the pendulum between angle and force. Here's what that transfer function looks like. In this equation, lowercase m represents the mass of the pendulum, and uppercase M represents the mass of the cart, or the car. G is the acceleration of gravity, L is the length of the pendulum, and I is the moment of inertia of the pendulum. Now, the force from the car that will be the input to the pendulum will come from the voltage in the car. So we have not only a transfer function between the angle and the force for the pendulum, we also have a transfer function between voltage and force for the car. But for today's example, I'm going to ignore this part of the transfer function that converts voltage to force. I'm going to do that simply in order to keep the equations small enough that we can see what's happening as we put this into a feedback block diagram. But the procedures that we're using today work just as well with an additional element in the system that converts voltage to force. For today, we're only going to use this part of the transfer function that converts force into angle. Let's put this transfer function into Matlab and see what happens. First, I'm going to put in values for all of my constants. And I'm going to keep track of what units each of these constants are measured in. I also need to calculate the moment of inertia of the pendulum. I look up the equation for the moment of inertia of a rod rotating about its center point, which is how these equations were derived, and I put that equation in here. Next, we also have this variable q that we used in the derivation of the transfer function, and I have to calculate the value of q. Next, I can put in my system transfer function, and I do that using the sys equals tf that we've used in lab before. The numerator in our transfer function just had m times l, while the denominator had qs squared plus 0s plus this constant which I've entered here. Let's take a look at what the step response of this will look like. Remember what we're expecting it to look like. It should show the pendulum falling over when we apply this sudden voltage, or in this case sudden force, to the car. Here's what the step response looks like. It shows that the amplitude, that is the value of the angle, our output, over time goes off to basically infinity. Now we know that the pendulum can't actually do this. The pendulum will hit the ground, but this is basically showing that the pendulum is going to fall, which is what we intuitively expected. So things appear to be going well so far, except that our pendulum does in fact fall over. What if we don't want the pendulum to fall over? Could we make a system that would control the car in such a way that the pendulum does not fall over? The first thing we would need to do is to add some feedback to our system. So we need some feedback. Let's suppose that on this pendulum we are going to mount an accelerometer. This accelerometer will detect the angle of the rod and will convert it to a voltage. Let's add the accelerometer into our block diagram. So far, we have the pendulum, which is converting a force into an angle. We also have a part of this block diagram that is a motor, and for now, this is the part where we're ignoring its transfer function in order to keep our equations a little bit simpler. But in here, there's another block that is converting voltage into force, and that's the motor. Now we have a new block that's converting the angle into a voltage, and that is our accelerometer. Now let's suppose that we hook up this accelerometer to the same circuit that is controlling this motor. And let's say that we hook it up so that the voltage reported by the accelerometer gets subtracted from the voltage that we're going to be sending to the motor, so that what we give to the motor is actually the difference between the voltage, let's say from our battery, to the motor. I'm going to call this signal error because it's the difference between the voltage from the battery and the voltage coming back through the accelerometer. This is the same kind of a setup that we saw previously when we looked at feedback for the centrifugal governor. Will this solve our problem? If we have the accelerometer in this kind of a loop, will this balance the pendulum? Let's see if we can figure that out. Let's suppose that this accelerometer directly converts angle to voltage. That is, 1 degree of angle converts to 1 volt. What will be the complete transfer function of this whole system? We'll use our block diagram reduction method. We'll start by taking the transfer function of the forward loop, the pendulum, remember that for now we're ignoring the transfer function of the motor converting voltage into force. We're only doing that to simplify the equations. This same method will work if you add in the other transfer function. Since we're assuming that the accelerometer directly converts angle into voltage, its transfer function is simply 1. So when we multiply this transfer function by 1, we get the same thing. This is the complete transfer function of our system with feedback. I'm going to simplify this system a little bit, and then let's take a look at what the step response looks like of this system. To help me reduce this system equation into our transfer function form, I'm going to start by multiplying the numerator and the denominator by qs squared minus m plus m times mgl, this whole denominator. What I get out at the end looks like this. This is my new transfer function. Does this system succeed in balancing the pendulum? Let's go back to Matlab and put in this equation and see what the output looks like. Here we are back in Matlab. I'm going to change my transfer function so that it is the transfer function of the new system with feedback. The only difference between the two systems is that the one with feedback has this additional m times l term in the denominator. Does that successfully balance the pendulum? Here's the step response of the new system. We can see that the pendulum is still not balanced even though we've added in feedback of the accelerometer. If we think about this just intuitively, we can see why. The sensor will eventually cancel out the drive voltage that we've applied, but not until the rod has already fallen. What we need here is a controller. A controller is another system that we can put in line with the system that we already have in order to change the behavior of the whole system overall. Let's take a look at what a controller looks like in a block diagram. We still have our original system, which converts voltage into an angle. Here, I've lumped together the pendulum and the car together in system. We also still have our sensor feeding back. However, we can now have another block, our controller, which converts something else into voltage. The controller converts error into voltage, and here our error could be whatever units we want it to be. So let's have our sensor feeding back the actual angle. The feedback from the sensor no longer has to be voltage in order to be subtracted from the voltage that is applied to our system. We could take the voltage produced by the sensor and do a calculation on that in order to get it back into degrees. Then our input to this system can be an angle. We subtract the actual angle from our input angle in order to get error, the difference between the angle that we want and the actual angle that the pendulum is at right now. This way, we can control something specific, like the angle of the pendulum, even though the input to the original system is the voltage to the car. The controller has an input signal of error and an output signal of voltage to the car, so the controller has the ability to change the voltage to the car in response to the pendulum starting to fall over. Physically speaking, a controller is usually a bit of circuitry that we connect to our system. For example, we could have something like a PIC chip, or a PSOC, or an Arduino, or something similar. In fact, that's why these things are called microcontrollers. They are tiny controllers. We program the microcontroller with a variable that says what angle we want the pendulum to be at. Then we connect up the sensor to the microcontroller. The microcontroller reads the sensor, subtracts the sensor value from the angle we want the pendulum to be at. Then it calculates the voltage to the car and produces the voltage with something like a PWM pin. So what kind of calculation should the controller be doing with the error to get the voltage? In other words, what should the transfer function be in this controller block? We don't know right now, but there is a good standard place to start. Let's assume that the controller should do some calculation with the error, some calculation with the derivative of the error, and some calculation with the integral of the error. That sort of calculation would cover all of our bases. So the transfer function should look something like this. We want to have the voltage to the motor be equal to some kind of a value times the error, plus some kind of a value times the derivative of the error. Or let me write this as E dot, since we've been using dots to represent derivatives. And some kind of a value times the integral of the error. So let's take the Laplace transform of this. The voltage as a function of S would be Kp times the error as a function of S. I have an S in this term since we have the derivative of the error, And here I have an s in the denominator because of the integral of the error. Now my controller has error as the input and voltage is the output. So the transfer function of this will take error as the denominator with voltage, the output, in the numerator. This is kind of a strange form, so I'm going to change it so it looks a little bit more familiar as a transfer function form we're familiar with. And the way I'm going to do that is by multiplying each of these two terms by s over s, and then all three of these terms will have the same denominator. This is the transfer function of our controller. This kind of a transfer function for a controller is commonly called a PID controller. P is for proportional, I is for integral, that is the part of our controller that is the integral of error, and D is for derivative, because we also had a part of this transfer function that deals with the derivative of error. So what is our whole system transfer function now with the controller in the block diagram? Let's use our block diagram reduction technique to find the transfer function of this whole system. In the numerator, we'll have the plant times the controller. There's the plant, and then here's our controller. In the denominator, we'll have 1 plus the plant times the controller times the sensor. And for now, we're assuming that the sensor still directly converts the actual angle into the reported angle. So the transfer function of the sensor is just 1. Going to simplify this a little bit and once again put it into nice transfer function form. I'm going to do that by multiplying the numerator and the denominator by everything that's in the denominator. That is qs squared minus m plus m times mgl times s. That will get rid of these terms in the denominators in both the numerator and the denominator. This is the transfer function of my whole system with the controller. I don't yet know what the values of Kp, Ki, and Kd might be, but that's okay. We'll do some simulating of the system and figure out what they should be. For now, I'm going to take this transfer function and put it into Matlab. In Matlab, I need to add my new constants that are now part of my system through my controller. I don't know what they should be, so I'm just going to set them all to 1 and see what happens. Now, I need to change my transfer function so that it is my complete system transfer function with the controller in the loop. So here's my new system transfer function. I still have step sys here to calculate the step response of the system. But before we look at it, let's take a moment to think about what a step response to this system means now. Remember that our input to the whole block diagram is the angle of the pendulum. A step input is like reaching out with my hand and pressing on the pendulum to try and tilt it to a constant angle. An impulse input would be like reaching out my hand and tapping on the pendulum to try and knock it out of position. So let's start out by looking at the impulse response. Since it's likely that reaching out and knocking the pendulum to try and knock it over might happen, let's see how this system would respond if that happened. Here's the impulse response. As you can see, the pendulum is still simply falling over if we reach out and tap it with our hand. So the PID controller didn't do any good for us. But don't worry quite yet. Remember that we simply set our P, I, and D gains to be 1 because we didn't know what they should be. This kind of a response is an unstable response. It just goes off to infinity when we give our input. One way to try and correct that with a controller is to increase the Kp gains. Let's try and set Kp to 10 and see if that changes the impulse response. This is a little bit better because it doesn't just go off to infinity. But this response is not much better because it's still going to enormous angles. The pendulum would, in reality, simply hit the ground. Let's try and increase Kp a little bit more. What if we made Kp to be 20? This is better yet. This time, the pendulum is balanced. When we reach out and knock the pendulum with our hand, it will swing one way and then swing the other way, but it will eventually settle on 0. 0 is the angle that the pendulum is at when it's straight up and down. This is showing us that if we had a PID controller with a Kp value equal to 20, the pendulum on a cart would be able to balance the pendulum when the pendulum is disturbed. However, the pendulum is still swinging quite wildly, high and low. What would happen if we increased Kp even more? Let's make Kp 30. Did our response get better, or did our response get worse? When you are trying to find gains for a controller, you want to take note of whether your change made a positive improvement or a negative improvement. Let's look back at Kp equal to 20. Here, the maximum amount of swing in the pendulum is above 6 but below 8. It's about 6.8 or so. What happens when we make Kp equal to 30? Here, the peak is even higher. So going from 20 to 30 did not improve the response. What happens if we increase Kd? Let's make Kd 10 and see what the impulse response looks like now. The characteristic of this response is very different. Here, when we tap the pendulum, it will swing wildly far out of its position, but then it will start to come back and it won't oscillate anymore. Is this a better response or a worse response? Partially it depends on how far out of its position the pendulum can get before it will no longer be able to be caught. Here's the response for Kd equal to 5. And here's the response with Kd equal to 5 and Kp equal to 25. You can see that as we change the values of each of these gains on the three parts of our controller, the response of our pendulum changes. Here's the response to Kp equal to 15 and Kd equal to 2. This process of finding values for the controller gains that will give us a response that we like is called tuning. There are more scientific defined methods for finding good gains for a controller, and if we have time, we'll take a look at some of those in this class. However, in practice, much of the process of tuning gains is very similar to what we're doing here. We try different gains in a simulation until we find a response that looks good. Then we can go and use those gains in our physical controller and watch the actual response of the system. We modify the gains by small amounts until we find a response of the system that behaves well in practice. Today we saw how a controller can be used to modify the output of the angle of a pendulum given the input of voltage to a cart. But this little trick can be used for all kinds of systems that we want to behave differently than they currently do. By adding a controller in the loop, we can get the output behavior of the system to be much better than it is without the controller, and we can get the output to the system to generally match whatever kind of behavior we decide is good behavior for that system.